Hi, this is Jenna Guerin. I'm going to be presenting my second case study. It is August 22nd. So I'm going to start with case number 2. So first we have in the liver, glucose is taken up by GLUT2, which is insulin independent, and GLUT2 functions for rapid uptake or release of glucose. So this diagram just shows glucose entering through GLUT2 to the hepatocyte. Once it's in the hepatocyte, glucose kinase is going to catalyze the phosphorylation of glucose to glucose 6-phosphate, which eventually will go into pyruvate. In the muscles, glucose is taken up using GLUT4, which is insulin dependent. So when insulin binds to the receptor, which we can see here, it's going to activate GLUT4, which translocates to the membrane. Once it's on the membrane, glucose is able to enter the cell. And then when glucose is in the cell, hexokinase is going to catalyze the phosphorylation of glucose to glucose 6-phosphate. So since it's insulin dependent, increased insulin causes increased glucose uptake, resulting in increased glycogen synthesis. In the brain, we have both GLUT1 and GLUT3 for the uptake of glucose, and these are both insulin independent. So over here we see GLUT1, and GLUT1 really allows glucose to pass through the blood-brain barrier. Then we have GLUT3 over here, which allows for glucose to enter the neurons. So one important thing about GLUT1 and 3 is that they both have relatively low Km values, so they have very high affinity for glucose. This is going to allow for the continuous flow of glucose into the neurons even at low concentrations. Then once glucose enters the neuron, it's also going to be using hexokinase to catalyze the phosphorylation of glucose to glucose 6-phosphate. In the adipose tissue, it's pretty much the same mechanism as in the muscle. They both use GLUT4. So they both need insulin to bind to their receptor, so GLUT4 can be translocated to the membrane. In adipose tissue without insulin lipolysis occurs, forming glycerol and fatty acids. The glycerol can then be transported through the liver via the bloodstream and converted to glucose there. So one important thing is that in all these tissues, phosphofructose kinase and pyruvate kinase are utilized ultimately to convert glucose to pyruvate to be used for cell energy. Phosphofructose kinase is induced by insulin and repressed by glucagon. It becomes activated by 5' AMP, fructose 6-phosphate, and fructose 2,6-bisphosphate. It's also inhibited by citrate, ATP, and glucagon. These all help in the maintaining homeostasis of the glucose uptake in the body. Then pyruvate kinase is induced by insulin and fructose and repressed by glucagon as well. It becomes activated by insulin and fructose 1,6-bisphosphate and inhibited by ATP, alanine, glucagon, and norepinephrine. So in this image, you can see a fairly uniform distribution of glucose on this side of the brain, which is what this is showing. But then you see the tumor site here. So the glucose uptake here is extremely concentrated. The tumor cells are utilizing more glucose than normal cells. In normal tissue, glucose uptake is fairly slow and regulated by the release of glucose into the bloodstream from the small intestines. In the tumor cells, however, they have unregulated glycolysis due to their uncontrolled growth and need for excess amounts of glucose. By taking up large amounts of glucose, they are meeting the cancer cells' energy needs for multiplication. So the cancer cells grow faster than blood cells are able to nourish them. This leads to tumor cells experiencing hypoxia and solely use glycolysis, leading to lactic acid fermentation to provide a source of ATP. This is also known as the Warburg effect. One effect of this is that since the cells are experiencing hypoxia, they begin to secrete angiogenic factors to stimulate the growth of new blood vessels. Here we see the hypoxia. It leads to HIF1, hypoxia-inducible growth factor, which is going to help make glycolysis more efficient because it's going to increase the expression of glycolytic enzymes over here and GLUT1 and 3, which is going to allow more glucose to enter the brain cells where the tumor is located. Then HIF1 also stimulates the expression of VEGF, which are vascular endothelial growth factors or angiogenic stimulators. So that's going to allow for more blood vessels to grow within the tumor so they can continue to get more nutrients. So in case 3, the patient described here has type 1 diabetes. Based on both the reports of the mother and the serum insulin levels, the patient profiles matches that of one with type 1 diabetes. In type 1 diabetes, there is autoimmune destruction of beta cells in the pancreas. The beta cells are in charge of producing insulin. So typically, as we see here, insulin is going to bind to the ligand and cause signaling cascade for protein translocation, enzyme activity, gene transcription, and cell growth. Without the insulin, though, the glucose that is absorbed into the bloodstream, which is what this diagram is showing, this is the normal use of glucose. The glucose is in the bloodstream along with insulin, and they are used together. Then when we look over here in type 1 diabetes, there is no insulin in the bloodstream. There's only glucose. So insulin can't bind to the cell, so then glucose cannot enter the cell. Since glucose is unable to enter the cell, it's going to stay in the bloodstream. And that leads to the symptoms of polyuria, dehydration, fatigue. The cells aren't getting enough energy that they need because of this. And it leads to an imbalance in blood regulation, and the kidneys are filtering the blood, creating more urine to try to get the glucose out of the bloodstream. So a normal fasting blood glucose level would be below 100 milligrams per deciliter. In this case, the fasting blood glucose levels will likely be above the normal range. Anything above 126 milligrams per deciliter is considered to be indicative of diabetes. This is for the similar reason as I just explained. When there's no insulin present, the glucose has nowhere to go but stay in the bloodstream, even when fasting. The glucose will be at a high level in the blood. So this is just a little chart I made with type 1 diabetes, fasting glucose. We're going to see higher levels of blood glucose. So anything above 126 is indicative of diabetes. A random glucose, when they take the blood glucose at any time, it's going to be above 200 milligrams per deciliter. And then after glucose load, which is one thing that they talked about in this case, the results are going to be well above 200 milligrams per deciliter because there's way too much glucose building up in the blood. Whereas for a normal blood sugar, we're going to see the fasting glucose be 100 milligrams per deciliter or below. The random glucose is going to be below 200, and glucose after glucose load is only going to be about 140 because your insulin is able to help this glucose get into the cells. So the regulatory enzymes that are likely going to be active here are glucose 6-phosphatase and fructose 1,6 biphosphatase. These enzymes are key enzymes in gluconeogenesis, or the production of glucose. Since cells are not able to use the glucose due to lack of insulin, the body cells are in a fasted state, triggering gluconeogenesis to produce glucose. So here we see glucose 6-phosphate is catalyzing the conversion from glucose 6-phosphate to glucose. And then we look down here, and fructose 1,6 biphosphatase is catalyzing the conversion of fructose 1,6 bisphosphate to fructose 6-phosphate. So these are really the key enzymes that are going to play a role in the production of glucose here.